Hello friends, let's look at the problem 3557 again. In this video, we are going to solve it using dynamic programming. So here I want to point out that in the previous video, we solved this problem using greedy construction. So here is the code. Actually, you can try this code or check out the previous video for more details. So here, again, I want to emphasize two things. First is that it's not necessary to use up all the strings. So here is an example, right? So the return is 1, but the one non-intersecting string can be any of the below, right? So you can also look at example 2. So in example 2, so this for is forms one valid one, and the whole string forms one valid one. But you cannot see the output is 2 because these two are intersecting, right? So you can identify this one by this one or this one. Both are okay, but the maximum number is 1. So the constraint is the following. The length of this word can be as long as 2 times 10 to the power 5, and the words consist only of lowercase English letters. So this actually simplifies the problem because for lowercase English letters, at most you have 26 unique letters in the word. So with that said, let's look at the dynamic programming solution. So here I'm going to copy this this part. So when you do dynamic programming, so actually it's important to notice the interpretation. So here let me write the DP interpretation. So here I'm going to have a DP table of length n plus 1, where n is the length of the word, right? So I'm going to interpret this dpi to be the maximum number of valid substrings we can construct, or one can construct using word, say, from 0 to up to I, right? So this I, dpi, because this word is going to have index 0 up to index I minus 1. If we write like this, it means that if same as max number of valid substrings, we can construct using length I prefix of word, right? So with that said, I guess if you know this, the main point to explain will be the DP update rule. That's our main focus next. So let's carry out this program. First, I'm going to have a character or dictionary. So basically, it's a collections of default. It's a dictionary, right? I'm going to default dict. So I'm going to have a container list. So this will be the unique characters and the indices they appeared in the word, right? Then n is the length of this word, and we can have DP table. So 0 times n plus 1. So we can write like this because each of the inner elements 0 is immutable. But for safety, you can always write like 0 for a dumb index in range n plus 1. Because we want to avoid modifying one affects others. But if you have some list, so you cannot write like this, right? So you need to pay attention, especially if you do higher dimension list. You need to pay attention to the way you initialize. Pay attention to mutability. immutability of the things. So once we have this, so now let's iterate over this word in enumerate word. As I explained in the previous video, we use enumerate keywords as due to the fact that we are going to track the indices. So first, I want to have dpi plus 1 to be dpi, right? What does this mean? It means that if using longer prefix, we could construct more, at least more than shorter prefix. Let's see, using longer prefix, we can construct a more valid substring than using shorter one, right? Shorter one. So I would say no less than. This is the more accurate wording, right? So let me maybe put it here, right? So this is the meaning of this dpi plus 1, because here dpi plus 1 is that how many valid non-intersecting substring we can construct using length I plus 1 substring. So here is using length I prefix, right? So now let's see. Let's first get the length or the last index. So the length character, so is C, right? So if you have the character pre-appeared, so you will have a length. So then J will be the last index. It's possible that the character hasn't appeared, so this length will be 0, then J will be -1. So then it's not going to enter the next while loop. So while J is greater than or equal to 0, right? So if this character hasn't appeared before, this length will be 0. Then we're not going to enter this while loop, right? So and J is greater than the length character C -4, right? So if J is too small, I don't need to consider, right? So because if it's less than this number, so only consider this character, we have already length 4. So then if I, so the current character, that is the character C, and the character C at the current index, so this will be a index where character C appears before. If this minus this one plus 1 is greater than or equal to 4, it means that we can construct one using this, starting from this index. So start index, this one, and the index I. So the end character will be C, right? The current character. So if this is the case, so we know that, so we have dpi plus 1. So this corresponding to the this I. It will be the maximum of dp, because this is the end index. So the end index, let's recover that character C and G, right? So because ending at I, the length is I plus 1, right? So that's why we are updating dpi plus 1. So ending at this index, the length will be this index, right? So in other words, so we are going to what we consider actually is before this one. So ending, we should so dp, the index before, right before, so it's one less than this one, right? this is the index, 1 less than this one, but the length will be plus 1, right? So this, in other words, the total effect will be this. Let me do this, -1 plus 1. That must be much better. So from this one, this is the maximum number of substrings we can construct right before this index. And then we can add 1, right? Because this is the one. Start from here and ending at here with character C. So then once we done this, so we can actually decrement J by 1, right? So then afterwards, so what do we do? So we actually character C append I. Because why we can do this rather than first do a linear scan of the word to get the character, because for each index I, we only need to look at the previous occurrences of the corresponding character, right? So then we actually can return dp -1, right? So let me first run it. Yeah, it passes all the cases. So because in the previous video we have analyzed the outputs, now let's directly submit that. Yeah, so which part we are exacting. So let's change this one to VV. Let's submit. Make sure we are checking the current one. Yeah. So first, the comment is that I think for the current way of writing this DP solution is not best, because it's not very slow, very fast. So you can further actually modify this, or if you want, you can actually introduce binary search here. This is one comment. Another comment is that you can do some variations of this DP solution, so that you can accelerate the full solution. Actually, I wrote personally several versions of DP solutions, but this one is good for teaching purpose, right? The last comment is that we have a large dynamic programming playlist in our YouTube channel. You're welcome to check out the playlist and do some practice, especially for dynamic programming. With that said, I guess that's it for the current video. Thank you for watching.